Hello friends, welcome to Susan and John MathTube. This is lesson number 25 in the examination preparation series, and we are still in differentiation under the integral sign, and in today's video we are going to learn something very important. Okay, so as always, the 5 golden rules. Point number 1, I hope you are doing this. Are you ready with a pen and a paper? And second thing, I hope you are working out all the problems along with us. That's very important. Unless and until you work out mathematics, you're never going to be confident in it. And of course, this is up to you. Point number 4 and point number 5 is very important. Test yourself. If you feel confident, take the past year's question paper, and try to solve the question. If you are able to solve, okay, that's fine. If you are not able to solve them by yourself, that means you lack practice. Okay, so with that, let's start today's video. And before we start, I'm going to teach you one trick. And the trick is called method of suppression. So look at this. Suppose we have a problem like x minus 3 times x plus 1, and the numerator is 2x plus 1. In class 12, you might have learned how to solve this with partial fraction. You will assume, let it be a by x minus 3 plus b by x plus 1, and keep on simplifying, etc. You find a and b. But we have one very powerful method, and the method is called method of suppression. And what we do is, we write like this, and then I look at the denominator of the first term, and tell me, when will this vanish? For what value of x will this become 0? Of course, x equal to 3. Of course, x is equal to 3. Now what I do is, I substitute this everywhere other than this term. I substitute this everywhere other than x minus 3. So I will get 2 into 3 plus 1, the whole divided by 3 plus 1, and that will be 7 by 4. So I can write 7 by 4 here. And next what I'm going to do is, I'm going to check the second term. Now tell me, when will x plus 1 become 0? Of course, when x is equal to minus 1. And now I'm going to substitute this x equal to minus 1 everywhere other than this x plus 1. So I get 2 into minus 1 plus 1, the whole divided by minus 1 minus 3, that is minus 2, that will be minus 1 by minus 4, that is 1 by 4, and I write that value here. So this is called method of suppression. Okay, now the condition to apply this is very simple. The degree of numerator should be less than degree of denominator. So what's the first thing? You check the degree of numerator and degree of denominator, and the degree of numerator should be less than degree of denominator. And point number 2, the numerator and denominator, if it contains x, it should be completely in x. If it contains x square, it should be completely in x square. If it contains x cube, it should be completely in x cube. I'll give you an example. 2x square plus 1 by x square plus 1 times x square plus 7. The degree of the numerator is 2, degree of the denominator is 4. Okay, first condition satisfied. Second condition, look at this. This is completely in x square. It's not a mixture of x square and x. This is not allowed. This is completely in x square. This is completely in x square. So this is valid for our trick. But if it is something like 2x square plus 1 by x square plus x plus 1, or no, this cannot be applied. Even if it is like 2x square plus 1 by x plus 1 and the next one is like x square plus 7, no, this is not qualified. Okay, now let's go for something little bit hard. X square by x square plus 1 times x square minus 2. Suppose you want to convert this into partial fraction, we can apply that awesome trick, that is method of suppression. So what we do is we write by x square plus 1 and by x square minus 2, and secretly I'm going to write t by t plus 1 t minus 2. So in the main step we write like this, and secretly we write this, and here I write t plus 1 plus, and here I write t minus 2, and always plus in between like partial fraction. So now tell me, when will this become 0? When t equal to minus 1. So I plug in t equal to minus 1 everywhere other than this. So that will be minus 1 by minus 3, that is 1 by 3. I will write the answer here, not here. I don't care about this. Okay, now tell me, when will t minus 2 become 0? Of course, when t equal to 2. And I plug in everywhere other than this. So I get 2 by 2 plus 1, that is 2 by 3. And that's it, my friends. We have converted this into partial fraction form. Once more, so that you can boost your confidence, let's try this problem. 1 by 1 plus a square x square times 1 plus b square x square. So what I do is I'll write in the main step like this, like this. Anyway, what is the degree of the numerator? 0. What is the degree of the denominator? X to the power 4 will come, because when you multiply this, so that degree condition is satisfied. Now in the numerator there is no x, there is no x square, fine, that's 100% fine. Look at the first term, it is completely in x square. Look at the second term, it's completely in x square. So we can apply the awesome method called method of suppression instead of the long process partial fraction. Okay, so I'm ready for the trick. So I'm going to write this somewhere secretly, like a side step, and I will write by 1 plus a square t plus 1 plus b square t. So tell me, when will this vanish? For what value of t? T should be equal to minus 1 by a square. Now I substitute that everywhere other than this, and I get 1 by 1 minus b square by a square. Take LCM, flip it, you get a square by a square minus b square. If you want, you can write it here, but I prefer to write the answer here. Okay, now tell me, when will this become 0? Of course, t is equal to minus 1 by b square, and I plug in here. So we get 1 by 1 minus a square by b square. So we get b square by b square minus a square, which I can write as minus b square by a square minus b square. Of course, I am sure you understood this. It's not rocket science. I just made a minus b into b minus a, so the negative came. Okay, so let's start with the question. So please write, please mark it important. Write please. Evaluate the integral 0 to infinity tan inverse ax the whole divided by x times 1 plus x square dx. So as always, the variable of integration is x and the parameter is a. So I'm planning to differentiate with respect to a. But before that, let's make a few things very clear so that even the weakest of the weakest students will find it comfortable. What is the derivative of tan inverse x? 1 by 1 plus x square. What is the derivative of tan inverse a into x? 1 by 1 plus ax the whole square times a. Wait a minute. What is the derivative of tan inverse ax? I mean not d but curly d, the partial with respect to a. Can you answer that? 1 by 1 plus ax the whole square times x. Because when you perform partial differentiation, a will be the only variable because we are differentiating with respect to a. And that means x is a constant and a will be the variable. Okay, now let's start, and I hope you don't mind if I write the given integral as 1 by x times 1 plus x square and tan inverse ax over here dx. It's the same thing. I just wrote that so that integration the differentiation will go fine. Now as usual and as expected, I'm going to write applying Leibniz rule on both sides to differentiate with respect to a. We get integral 0 to infinity. This is a constant because when we do this step, only our a will be a variable. And you saw the derivative, so ax the whole square times x dx. So I'll write it neatly after simplification because x and x will get cancelled. So di by dA is equal to integral 0 to infinity 1 the whole divided by 1 plus x square times 1 plus a square x square. I'm sure you're going to understand why I taught you method of suppression. So what we do is we are going to convert this. So I'm going to write di by dA is equal to integral 0 to infinity. I'm going to wait for your answers with the awesome trick method of suppression. If you don't like method of suppression, you are free to use partial fractions. Okay, so the trick. I will write 1 by 1 plus t. By the way, are you allowed to use the trick? Yes, the degree of numerator is 0, denominator is 4. And numerator does not contain anything, perfectly okay. Denominator contains x square, only x square. So we are eligible for the trick. And I write like this. Tell me when will this become 0? When t is equal to minus 1. So I put everywhere else, we get 1 by 1 minus a square. And when will this vanish? When t equal to minus 1 by a square. And I put it everywhere else, we get 1 by 1 minus 1 by a square, that is 1 by a square minus 1 by a square, so it goes up. So we get a square by a square minus 1. But I am going to write this as a square by minus of 1 minus a square. I am sure you understood why, because that will come common. So time to write 1 by 1 minus a square and minus a square by 1 minus a square. I hope you got the answer by yourself. Now let's keep the constants outside. So di by dA is equal to, by the way, you have to write one more important point. This is a improper integral. And you can write improper integral type 1. And we will cure that improperness also. At the same time, I am going to take that constant outside. And for the improper integral part, I will write limit t tends to infinity, integral 0 to t. Lot of things are going on. I hope you're able to understand. If you need clarification of any step, just log on to my website www.sjmathtube.com and you can talk to me directly in the messenger. Minus a square 1 by 1 plus ax the whole square. Okay, a lot of things. So I took the constant outside and I cleared that improper part and I wrote the remaining part. I hope you're okay with this. Okay, now time for some add-ons. So the first thing, integral 1 by 1 plus x square. I'm sure you remember the derivative of tan inverse x is 1 by 1 plus x square. So integral 1 by 1 plus x square will be tan inverse x plus c. So what about integral 1 by 1 plus ax the whole square? It's very simple. Tan inverse ax the whole divided by a plus c. So in the next line, what happens is we get 1 by 1 minus a square, limit t tends to infinity, and time to integrate. This will be tan inverse x minus keep a square, and the second part become tan inverse ax the whole divided by a, where x varies from 0 to t. So this a and a will get cancelled. So we get 1 minus a square, limit t tends to infinity. Let's plug in the upper limit. So we get tan inverse t minus a tan inverse at. And I'm not going to plug in the lower limit because I know this will be 0. And tan inverse infinity is 90 degree or pi by 2. So we get di by dA equal to pi by 2 minus a pi by 2. So we get di by dA equal to, look at this, 1 by 1 minus a square is outside, and we know that tan inverse infinity is pi by 2. So we get pi by 2 minus a pi by 2, and this denominator becomes 1 minus a. I hope you remember what is 1 minus a into 1 plus a, and pi by 2 comes common and 1 minus a, cut. So yeah, we get di by dA equal to pi by 2 1 by 1 plus a, isn't it? So the usual question, now I'm not going to talk about that. I asked a lot of times and I hope you are not having any problem. So we get I. Yeah, by the way, I'll definitely ask one question. What is the derivative of log x? 1 by x. So what is integral of 1 by x? Log x. So what is integral 1 by x plus 5? Log x plus 5. So the answer is log 1 plus a plus c. And I'm going to call it equation number 1. Now time for our box. And in the box, I'm going to write our question. I hope you still remember our question, integral 0 to infinity, tan inverse ax, the whole divided by x times 1 plus x square dx. And I did differentiation with respect to a. So I'm going to ask myself, if I put a is equal to dash, I will be equal to 0. As simple, that's 0, because tan inverse 0 is 0. Now I plug in all these things in equation 1. So I write by equation 1, I have to put I equal to 0, and that will be pi by 2 log 1, that is 0, plus c. So c is equal to 0. That's it, my friends. Now you can write the answer by 1. I is equal to pi by 2 log 1 plus a plus 0. Yeah, that's it. Now let's do another important question, that is evaluate. Please mark this also important. integral 0 to infinity log 1 plus a square x square, the whole divided by 1 plus b square x square. Please mark all these questions important. And I have to tell you something very important. Many students, especially first year, first semester engineering students, have trouble with these problems. And that is exactly why I am not skipping anything. I am doing most of the problems that has been asked in the exam. You can check your past year's question paper and you'll find these questions. And if you really want to solve these problems in your exam, you have to practice these problems again and again and again. That is the only way you'll be confident. That's the only way you can perform properly in your exam. In case you're ever overconfident, because I have seen many students asking me, why should I repeat the same question again and again? Isn't it boring? Okay, it might be boring, but take a look at the past year question paper. They are asking the same question. So, if you really want to do that, you have to practice. And you ask any mathematician in the world who is interested in solving problems. I'm not talking about the application part, or I'm not talking about the historic part, or I'm not talking about the theory part. But if you want to be very good with the problems, you have to practice again and again and again. And with that, let's start this problem. Okay, so we have a variable x and the parameters are a and b. In lesson number 22-23, I kept on saying if you want, you differentiate with respect to a, and if you want, you differentiate with respect to b. But this time I'm going to be adamant. I want you to differentiate only with respect to a, because you won't get any benefit if you differentiate with respect to b. Think about it. If you get the answer, you can put it in the comment box below. If you did not get the answer, feel free, email me, talk to me. I'll repeat once more. We have a and b. In the previous questions, I always used to comment, okay, you go ahead, differentiate with respect to a or b, you're going to get the same answer. But this time, I'm sorry. Don't do with respect to b. You may not get the answer easily. So, I'm going to write I, and I'm going to differentiate with respect to a. I already told you the plan, but let me write this a little bit neatly so that our differentiation becomes easier. By the way, what is the derivative of logarithm of x? 1 by x. In the assumption, the base is e. In the assumption, we are talking about natural logarithm. And I'll repeat once more the fact. Nowadays, if you look at any American book or any standard books, they write ln x instead of writing log x to the base e. But long back in the calculus books, the common assumption is logarithm is to the base e. But nowadays, if you write logarithm, people understand it is to the base 10. Anyway, I'm not going to change the pattern in the books under TU University, so it's okay. Yeah. Now tell me, what is the derivative of log x? Of course, 1 by x. What is the derivative of log smiley? Of course, 1 by smiley, wait a minute, times the derivative of our smiley. So, are you ready to differentiate with respect to a? Yeah. So, I get di by dA is equal to integral 0 to infinity 1 by 1 plus b square x square. I can write up to this because this is a constant. I am differentiating with respect to a. So, log something 1 by the same thing times the derivative of this part. And please don't forget, a is our hero. So, we get 0 plus 2a into the constant. Is that okay? So we get di by dA is equal to this 2a goes outside, we get integral 0 to infinity x square by 1 plus a square x square into 1 plus b square x square dx. So as before, time for partial fraction. Degree of numerator is 2, degree of denominator is 4, degree conditions are okay. I see x square, x square, x square everywhere, so the second condition is also okay. So time for partial fraction. So I'm going to write something secretly. So I'm going to write t by 1 plus a square into t 1 plus b square times t, and I'll write 1 plus a square into t plus 1 plus b square into t. Now tell me, when will this vanish? When t equal to minus 1 by a square. And I put it everywhere other than the first term, so I get minus 1 by a square by 1 minus b square by a square. So we get minus 1 by a square minus b square. So I'm going to write minus 1 by a square minus b square. And now I put t equal to minus 1 by b square here. So I get minus 1 by b square by 1 minus a square by b square. So that is equal to minus 1 by b square minus a square. And as always, I want a common factor, so I'm going to flip it. I'm going to write 1 by a square minus b square. So that's it, my friends. See, we are ready with the answer. So I'm going to continue. Okay, now what we do is we use these values. So I'm going to write 1 plus a square x square plus 1 plus b square x square dx, and I take that values, minus 1 by a square minus b square plus 1 by a square minus b square. So we have something common. Let me take the common and let me cure this improperness. So I'm going to write di by dA is equal to 2a. Okay, time to make it a proper integral. T tends to infinity, integral 0 to t. Okay, now this is going to be common. I should have kept it outside. So I'll write by a square minus b square. And I'm going to write the positive term first and the negative term second. So we'll get 1 by 1 plus bx the whole square. You will understand this only if you are trying to solve the problem by yourself. Okay, so now that's it. Now you can just relax. 2a by a square minus b square. So tell me, what is the integral of this? We just discussed this integral in the previous question. Tan inverse bx the whole divided by b minus tan inverse ax the whole divided by a. And of course, the limits are x equal to 0 to t. So time to plug in. And no need to plug in the lower value because tan inverse 0 is 0, so this will vanish. So we get di by dA is equal to 2a by a square minus b square, limit t tends to infinity, tan inverse bt by b minus tan inverse at by a minus, of course, when you plug in the lower limit, you will get 0 minus 0. Okay, I know the fact tan inverse infinity is 90, and now I don't want you to waste more steps, so we can skip a few steps and write pi by 2. This will become pi by 2, this will become pi by 2. So pi by 2 comes common and you get 1 by b minus 1 by a. and we can factorize this. We can take LCM here. So di by dA is equal to 2a by a minus b, a plus b, and pi by 2 remains as such, but more action over here. It will be a minus b by a into b. So this and this gets cancelled. So di by dA is equal to, okay, our pi by 2 is still there. Oops, I forgot to cancel that too. So we get, yeah, we have more things getting cancelled. It's more exciting. So we get pi by a plus b. Yeah, and b is also remaining. Yeah. So we get pi by b into a plus b. So the usual questions, what are you trying to find? I. And what did you find? Di by dA. No need to worry. So we get a differential equation, pi by b, 1 by a plus b dA, and integrate. Did you understand why I kept this outside? The variable of integration is a, that means b is a constant. And the derivative of log x is 1 by x. So integral of 1 by x gives me log x to the base c, of course. So integral of 1 by x plus constant is actually log of x plus constant. With that fact, I'm going to integrate with respect to a. So that means a is the variable of integration. So I get log a plus b plus c, and as always, equation number 1. Okay, so time for the box, and in the box I'm going to write the question. Integral 0 to infinity log 1 plus a square x square, the whole divided by 1 plus b square x square dx. Okay, come on, tell me. Put, I did differentiation with respect to a. Okay, put a equal to dash. Give me capital I equal to 0. Very simple. Put a equal to 0. This will vanish. We will create log 1. Log 1 is 0. Numerator is 0. That's it. So I can write by 1. Now I'm going to plug in that value. I'm going to put 0 here. We get pi by b log 0 plus, instead of, okay, log b plus c. That gives me c is equal to minus pi by b log b. I hope you also got the same answer. Now the last step, by equation 1, I is equal to pi by b. Where is equation 1? Yeah. Pi by b log a plus b minus pi by b log b. Now this pi by b will come common, and what is log a minus log b? Log a by b. So that's the final answer, log a plus b by b. Okay, that is one really long problem. Once more, I'll recommend practice the same problem once or twice till you are confident. So my friends, I'll be back with a very important question in the next video. We'll be doing only one question. That's a long one. That's an important one. So we will meet tomorrow with another question, another important question in differentiation under the integral sign. And as always, if you like the video, please share the video with your friends. And we will meet soon. Till then, my friends, bye.